Quantum. With me today is Ruhan. Ruhan is the lead developer on the Quantum Bot SDK. And together we will implement some bots into a little quantum game we have created.
Hey, welcome everyone. Nice to meet you. Let's talk about quantum and AI, and feel free to ask questions about AI and quantum itself if you want, and we'll be checking those and answering live stream.
Yep, so how about we get started and tell the people here a bit about the Bot SDK, Ruhan. So what is this about? When should people use it? Yeah.
There's this one thing very important about online games, that is AI, because when you're playing online, when you're using your game, you need good ways to test your game when you don't have that much people yet, or for when you release your game and you still don't have this much big player base that can fulfill all of the rooms. So sometimes people can wait too much or have to play alone with. So because the game has to get traction and it takes time. So AI is this very complex and important topic for online multiplayer games. And because of that, we decided to develop a SDK on ourselves, the Bot SDK, which is an AI tool that we provide with Quantum specifically and Unity in order for you people to make games which has AI in a quicker way. Because AI can be very complex to build. Sometimes you have a team of game designers or level designers and stuff, and they need to be able to change how the AI behaves and so on. Or maybe you need to be able to do fast prototyping, and all of this basically requires you to have a very solid AI architecture, and especially a editor that allows you to create AI with visual tools, not only by code, so everybody can participate and make the development progress much faster. So that's what we did. That's what we do actually with Bot SDK. It's basically two set of tools. The first one is the visual editor. So we have in Unity something like this editor that you can create nodes, then you can link stuff. You can say, hey, this is my AI document. Yes, thanks, Luke. So that's, for example, a stage machine. I'll be explaining what a stage machine is briefly, but basically you have this visual editor where you can define nodes and transitions and actions. So as you can see, there's a limit here. So people will be creating code to make these things possible. But once the base of the code is created, then designers and everybody can hop in and help building the AI. And it's really good because you can start making AI fast. And it's also good for maintenance. So in the long run, you can just be tweaking stuff in the editor and then you compile, and then that's it. The AI is now behaving very differently. Then you can create lots of AI documents. Maybe you want AI for very different things. So that's all possible. We're always improving the Bot SDK to encapsulate all of the things that we can make with AI, basically. And it can also be used for a few other things other than AI. We know that people use Bot SDK to actually create stage machines for, let's say, combo patterns in a fighting game, for example. So they find this state, the character will be punching in the air, and the other state he will start jumping and stuff like that. So yeah, you can use Bot SDK either for AI or for game systems in general, because, well, it's a visual editor. It's useful for everybody. The Bot SDK also has a very useful tool, which is the debugger. So you can in runtime see what happens with the game. Yeah, I don't think we have a GIF for that in the documentation in that page specifically, but you can see in runtime which is the state that is being executed now, which are the transitions that were taken. So you can see what happens, and then you can adjust, because we know that debugging also takes a huge amount of time when you are coding new stuff. So we also have debugging tools for this visual editor. And the other very important part for the Bot SDK is the actual deterministic code for AI that we have built with Quantum. So we have 4 AI models in there currently. We have hierarchical finite state machines, which is that one. And it's basically defines, you can define that this agent will be in a single state or in a set of states depending on the hierarchy at the single moment. So let's say that I start a game and I'm in idle because I don't know what to do yet. So this is a state. This is a state of idling. And then from idle, I might have a transition to chasing somebody if I see somebody, or maybe from idle, I'm gonna go chase an apple because I'm hungry. So basically the state machine allows you to define states, to define transitions that are possible from that state. And every state has a set of actions. So what do I do when I am these states? So when you're idling, probably you want to do anything. But when you're, for example, chasing a target, you have to execute code that actually makes the agent move in the direction of that target. So that's the state machine that we have, and we have it in a improvement. So we made it hierarchical, meaning that every state that you have can also have a set of substates. So for example, maybe chasing a target is not as simple as having just one state. Maybe it's complex. Maybe you need another state machine to define. So how do we chase a target? Should we look at people around while we do that? Should we attack him while we chase him? So that's the thing that we provide. It's hierarchical finite state machine. If you go down a little bit, Luke, you can also see the gulp. Yeah, it can. Let's show the behavior tree first. It's simplest to explain it. It's more similar to the state machine. So we also have behavior trees, and this is basically for a single agent, you have a few paths that can be taken when it's making a decision. So what should I do at this frame? What should I do? Should I also, let's use the same sample. Maybe I'm idling. Should I follow a target or should I go and get some food? So the behavior tree works in a way that you define to the leftmost branches what is the most important thing that matters to you to analyze first. And then if that's not the path that you want to take, then the behavior tree will, okay, so let's go and analyze the next branch until the tree actually finds something that it can do and it wants to do. So the behavior tree is about that. It's about choosing left or right until your agent is performing some actions. For the behavior tree, for this specific implementation with Bot SDK, we made it a stateful behavior tree, meaning that it's we are caching a lot of things in runtime to make this agent to run quicker than expected. So instead of having to analyze the entire tree every time that the behavior tree is executed, it has a few cached values, so it knows, okay, this is where I stopped, so I can just continue from here. So this means basically that we optimize the CPU performance of the behavior tree. It consumes more memory because it's a stateful behavior tree. You have to cache more data, so it makes it more data to store, but it's fast. It's not faster than the HFSM, but it's still very fast, and it's also very good. A lot of people love behavior trees. If you don't know behavior trees, maybe you should try it with Bot SDK. So yeah, that's what we have for behavior trees. Let's show now the gulp upwards. Yes.
And here it's important to note that if you are under the global game jam, the multiplayer game jam trial, then you only have access to the HFSM and the behavior tree at the moment.
Yes, because the gulp in utility theory, which we were talking briefly, they are in beta stage, so they are not production ready yet. So we are still progressing with them. So yeah, you only have two available unless you are a subscriber to the circle. Then you have access to all of the experimental features. So yeah, so we have GOAL, which stands for Goal-Oriented Action Planning. And so just giving here a brief comparison with the HFSM and the behavior tree, as you saw in the HFSM, for example, there is a lot of linking between everything. So from a state, there's a lot of linking to other states and so on. So there is a lot of linking. It's a very rigid structure. And it's kind of the same thing with the behavior tree. You have to define what are all of the possible branches that can be executed. So these both are true. These both solutions are kind of too rigid. But sometimes people want to go with something less rigid, something that can plan for itself. What are the possible things that can be done, and you don't even define it in a very strict way. So that's one of the main reasons why people use the GOP, the goal-oriented action planning. So basically, why this name, right? So goal-oriented. So you define for your agent, hey, this agent's goal is to open this room. So to open this room, he has to open the door. He or she has to open the door, but the door is locked, so you need to find the key. So, but the key is hidden, so you have to look around. So basically, you just tell your agent what is the goal. The goal is to open the room. So that's all you have to say, and then you have a set of goals and actions that the agent will take. Okay, what are all of the possibilities here with my goals and actions that I can, in order to create a bigger plan on how should I open this room. So then, as you can see in the editor, there is no linking, there is no transitions between things. That's just because the agent will just take everything that it can to create a valid plan to make the thing successful. So the GOP is interesting because of that. A lot of people like it too. It can be a bit, but it's very different if you're using GOP instead of EDFSM and behavior trees, because it's a different way of thinking in things, but it's also really good. It's also kind of popular model of making AI. And to finish this presentation of AI models, let's showcase the utility theory down there. So the utility theory is kind of similar to the GOP when we talk about not predefining everything that is possible for the AI. So basically, the utility theory, it uses math models instead of rigid definitions. So why utility theory? Because the agent will ever try to define, okay, so what is the most useful thing that I can do right now based on a mathematical combination of facts that I've been pulling from the game states. So, for example, let's say that the utility theory agent can, at the moment, chase somebody or eat. Well, how should I decide which one to do? Then we get the value of current hungriness that the agent has. So am I very, very hungry? So if I am, maybe I should just ignore other targets and should just go get some food. Or if I'm not hungry, and if I'm in danger or somebody's in danger, maybe I should go for chasing a target instead. So we get this value. So is it how hungry am I? Have I zero hungry, or is it one hungry? Is it 100% of hungry? So we get this value, then we insert it in a response curve. So you can model the curve to say, hey, for this range of value from 0 to 1, this is how important this thing is for me right now. So that's a very basic summary of the utility theory. We use values in curves in order to know what is the most useful thing to do, and then we do that. And it's more similar to GOP than HFSM and BT. So we have 4 alternatives for you to use. And also, actually, alternative is not a good naming here, because actually you can combine most of them. So for example, maybe you do some parts of your AI with an HFSM and other parts with a behavior tree and other parts with a GOP. So we provide everything. You just pick whatever you need and want or you like, and then you can build your game with it. So we have visual editors, and we also have deterministic quantum code for all of that. And this is basically what Bot SDK is all about. A few extra interesting details here is that bots are simulated here on the client side. So let's say that you're willing to make bots to replace, I don't know, 20 players because you only have 10, and then you have to create 20 bots. Well, those 20 bots, they are simulated in the local simulation for every client. You don't have to create a fake player which sends inputs and then the others receive the inputs in order to actually make the bot work. No, it's all simulated with quantum custom logic, which means that it's interesting that we don't increase the bandwidth usage in order to make it possible to use more bots. So the amount of bots here it doesn't matter in terms of bandwidth. It just matters in terms of how optimized your simulation can be. So it's also an interesting thing that we can do with Quantum, because Quantum is deterministic and only exchanges inputs. So that's interesting. So we usually have three use cases for AI, for bots, that you can maybe be using as inspiration for what you do during this game gen. So one of those things is the most basic and simple one. Not simple, sorry. It's the most common one, which is creating AI for NPC bots. So you have this monster. This monster has to chase your players and try to defeat them. So you can do that with Bot SDK. That's for creating NPCs. Or maybe you want to use it to fill your room with fake players. So during this game gen, even let's say you have your game for 16 players, but you don't get actual 16 people to try the game with you. Let's say you only get 6. Then you just create 10 bots on the simulation, and they will make the work. So you can test your game better instead of just having this gap of 10 players. And the third common use, is to replace a player by bots. So that's also very, very useful and very simple to do with Quantum. So let's say you have your 16 players in the game, but one of them rage quit the game, or I don't know, lost his connection and couldn't play anymore. So you don't want that entity to just lay there doing nothing. So you can also easily with Quantum just replace that player entity to be controlled by a bot, and it's seamless. And then if the player comes back, he or she can just get the control of that entity again and continue playing. So these are 3 very useful use cases. I suggest you to use them during the game jam. They are not very hard to do. We're going to showcase a few things here today. And of course, you can also ask, and they will be helping on how to achieve those things. Yeah, so thanks, Luke. That would be my initial introduction on the matter.
Yes, thank you, Juan. And yes, today we will showcase 2 out of 3 of the use cases you mentioned. So we will show you how to add additional bot players to a game, and then also we will show you how to replace players with a bot when they disconnect. So that's the plan. And for that, we have a little game prepared here. So this is a small quantum project we created. It's a super simple game where you're controlling this physics-based ball, and then you're just going through this 3D physics-based parkour, right? So you can use the ball and move the ball and apply force, and then you can jump, and your goal is really just to get, to the finish line. This is fully physics-based collision with deterministic rollback, so it always feels snappy and you immediately feel the impact even though you have high ping, and that's all correctly deterministically synchronized by Quantum out of the box. So that's really something that you can do very well with Quantum. And now this feels a bit lame doing this as a solo player, right? So we would like to add a bit of more bots to this so that it really feels like a multiplayer game. So before we get started with that though, let's go quickly over what we have here. So this has a game scene and a menu scene, and these are from the built-in scenes that come with Quantum. So the menu scene is the built-in menu scene that comes with Quantum when you download the SDK. And the game scene is also the built-in scene, but we added a few things like this map and a few of these NPC spheres that can roll into the player, but that's basically it. In terms of scripts, what we have is also pretty basic. In our Quantum code, we added a few components and a few systems. We have a player link component, which is similar as to what you get when you follow the Quantum 100. And then we also have some other stuff like a movement system, which this is a bit different from what you get when you follow the intro. Here we have a physics-based player, right? So this is not a KCC. This is actually applying force to a physics body. And as you can see, when we move, the sphere actually rotates. So we're applying angular velocity here, right? This is a rotating sphere. So this is just super simple code. We're getting the input from Unity, then we're applying force towards the direction. We have a jump button which applies an impulse, so a force that only lasts for 1 frame, so that you get boosted up into the air. Then we have a player spawn system. This is super simple. It's when we get the player data from Quantum, we instantiate an entity for the player, and we ensure that it has the player link that links from the player. Again, this is pretty much taken from the Quantum 100, so you can follow that. And then lastly, we have 2 more systems. One is a ground check that for each entity it checks whether it is grounded. So this is just so that we know whether we can jump or not. And then we have a teleport system. And what this allows us to do is define these areas here on the map, which are like these triggers, which they teleport entities when they touch them. So this one here, when the player falls down, we get teleported back to the beginning. So this is another super simple system. It just checks for this teleporter component, and then it uses a trigger collider to get informed when the player triggers this area, and then it teleports them to a target position. That's really all we have got here. And now we would like to add bots to this. So we have imported the bot SDK. You can do that by downloading the package from the documentation. And then we just added this to the project. And this gives us a few windows, which you usually don't have in Quantum. You can find them here. And this is the bot SDK editor. And now I'd say we start by, let's create a new HFSM bot. So what we do is go to new document, HFSM, and we will put that, let's put it into scripts, call it player bot. So this gives us a new visual state machine for the bot, right? Now, what do we like? Would we like our bot player to do here? I think for now we can just have him move forward, fall into the gap here. I think that's good enough. So we can say that the base state we have here is called move forward.
Yeah, just one note in that is that, as you can see, this node that comes by default, it has this default tag on top of it. This means that it's the first state that will be executed when the bot is initialized. So you can also change that if you create many states and then you want, okay, so the bot should now start with this one. You can also change what is the default one.
Exactly. Now, this alone will not do anything yet. So if we were to run this bot, this wouldn't execute any logic yet in this state. So what we want to do here, we want to say that while we are in the move forward state, we want to actually move forward, right? And now a very easy way to do that is to have the bot take control over the inputs, which instead the player would give. So right now, when we go to our Quantum code and we check the movement system, this gets the input directly from the player input. But what we can do is we can put a component in between there. So let's do that, and let's call it input source. And this is gonna store the player input. And then we can also have someone else apply input to this, like a bot, right? Anyone can update this component, basically.
Yeah, the cool thing about this pattern is that your input source can be anything, and then we can just reuse all of the player code for everybody. So let's say it's not anymore only for players, but it's for characters in general. Then, okay, maybe your input comes from player, maybe it comes from the AI, but then you can just reuse the same code. So you don't have to create like a movement code for players and another movement code for bots. Now, if you follow the pattern of just reutilizing whoever generates the input, then you use the same systems for everybody, then okay, bots and players will just move equally, and you won't have an issue happening specifically with one of the things because they're the same essentially.
Exactly. So what we did here is we replaced the input to take the input from this new component we created. Now we'll also just create a player input system. So this is going to be the case for the player object, where we just grab the input from the player and put it into this input source. So this will need a system main thread filter, and we're going to iterate over some components here, and this would be the player link and the input source, right? So each entity which contains both will be iterated over. Here, if you define these filters, don't forget to make the component pointers. It's very important. It's easy to trip up on this. And we'll need to make this unsafe so that we can use pointers. Then we can say we want to use this filter here. Now in update, all we want to do is we just want to set the input source input to the f get player input, yes. And we pass in filter.playerLink.player. This will give us a pointer, so we just need to dereference it, right?
Yeah.
So we're getting the value from the input pointer, and we're putting it, assigning it to the input of the input source. So this should work.
So we essentially have this layer in the middle now. Instead of just getting the player input, we put it on the middle layer, so we can also use the same middle layer for the AI. So we're essentially going to need two systems who know how to fill this middle layer of input. And that's the player one, and we're going to create the AI one.
Yes, exactly. And we're just going to run this at the very beginning, right? So that all the other systems which use the input, they're going to run after this. So we're going to put this before our other systems like the movement system. And now let's do the same thing for the AI, right? There we don't create a system, but we create an action. So an action is an asset, and this is going to be used by the bot SDK. Let's create the move forward action here. This is going to derive from AI action. And then I think we also need to make it serializable, right?
Yeah, so let me just give a quick explanation on this part. It's so bot SDK, the state machine is specifically, it works with AI action. So the AI action is what defines what is the thing to do when this is called. So AI action in Quantum is an asset. So the entire AI structure is compiled into a bunch of assets. So this gets translated in Unity to a lot of scriptable objects. So the entire AI model lies into the database itself. So it can be reused by many bots, and it's very useful to do it like this. So for everything that you want to specify, now this is an action that the bot should take, then you inherit from the AI action class. And then you get the override of the update method. So you can say, okay, this is what happens when this action is called, when the state is in there and uses this action. So that's what Luke's doing. He's getting the input source, which is the middle layer that we just created. And then he's going to say, he's created some kind of fake input. So the bot says, okay, the direction of this input in this bot is just moving up. So it just goes forward for now.
Exactly. So this is super simple. It's not as complicated as the player, which can move in all directions. So for now, we're just saying the AI moves forward. Now let's compile this and try to get this running in the editor. So I think just copy the bot out of it. It doesn't like something here.
The space. Can I see your code again? Oh, remove .assets from the namespace. Yeah, it's just namespace.
Yes.
Otherwise, our code generation will try to get stuff from where it doesn't exist.
Yeah, that's something I always trip over. They have to exactly.
Okay. We already have
and
a
now,
system which is updating the HFSM, right?
Which system do you mean?
Which updates the state machine?
Oh no, we will need to add that as well.
Yeah. Okay.
So first, when we are in here in this state, we can add an action to this update, right? So we're just gonna say move forward. So each tick or frame we're inside this action, we're gonna move forward, which means passing in the input towards the up or forward direction, right? Then once you edit this, always make sure to also compile it, else your changes won't be saved. That's something you can trip over, and then this will appear green when everything in the current document is compiled. But as you mentioned correctly, Juan, this is not running yet. First, we will need to set up a bot, and then also we will need a system which just controls AI execution in general. So let's start with the bot here. We'll take our player avatar, and we'll just try to rework this a bit into a bot. So we won't need the stuff we have related to camera, player color. Let's just remove all of this. And then instead, we will add the HFSM agent component. So this is used to control an HFSM bot. And here we can add this player bot. So this has been generated by the visual code we have before for the bot. With this, we're saying basically which of the many state machines you might have in a project should this bot use. Then the rest in here, we can just keep that empty for now. And in theory, this should already work. But now what we need to add is a system to control the AI. So let's create a new system, name it AI system. This will need to, we will need to run this every update on the main thread, right?
Mm-hmm.
And here we can get all agents, iterate over them, and then we call update on them. So we could also use a system main thread filter here, but we can also just define a filter like this. We can say frame.filter.
You can create frames on the fly, so it's also useful because sometimes people want a single system to update through more than one filter. So the other system type that Luke showed before, it only operates in one type of filter. So if you want more, well, you can just create a new filter on the fly whenever you want, and then you iterate through it. So that's a filter that goes through all of the HFSM agents that we have, that we're going to create on the scene. And then we have access to the components and to the entity of it.
Exactly. So here we're iterating over all the agents, and then we're just calling the HFSM manager update. This takes the frame. I think it takes frame.delta time. Entity, which we have here. And I think we also need, I think that's all right. Yes, that works.
Mm-hmm.
So this will update our agents each frame. And then the other thing we need to do is we need to initialize them. And the easiest way to do that is just when the HFSM component gets added to any entity, then we just initialize it immediately. So here the function is HFSM manager.init. And this one will need the root asset we defined here. So it will need access to this. So we will need to fetch this. And we can get this from the component here, right? So we can say root equals find asset, and this is an HFSM root. Then we get the reference to this from the data, right? Yes, data root ID.
So this is essentially defines a quantum asset, which we need during the process of initializing any state machine. We need to know what is the asset that defines this state machine, because as I told you, it has to know what is the default state and it's compiled in the asset. So we need to find the asset first so we can initialize. One thing also is that this update will be, as Luke said, it will update every HFSM agent every tick. But of course, you can optimize this however you prefer. Maybe you want to update only a few part of agents. So maybe if you have 100 agents, you want to update 10 of them on the first frame, another 10 at the next frame, and so on. So you can decide when to call that. So there are other openings to optimization just on how frequently you update your agents. It doesn't have to be every frame. It's your choice.
Exactly. Now, this system is all good, but as always, don't forget to add it to the system setup. So we will need to run AI at some point. I think here it's about at the similar time as we would process player input. So let's just put it here.
It's important because it's generating input, right? So it has to run before the systems that use input.
Exactly. And now when we editor, I think we're ready to have this bot running and just moving forward for now. Then we can optimize this bot so that it can actually solve this little parkour here. So if you press play, something.
Did you add it to the correct entity, the component?
Oh, this
this
needs an input source, and we haven't added that yet.
Yes, so we have this middle layer, which is the component that holds the input. So we have to tell the entities that they do have those components so they can write to it, and then this will be later used to be read from to actually make the input happen.
Exactly, and I think if I add it on the prefab, yes, it gets added on this copy here in the scene as well. So now if we try again, you can see the bot is rolling forward. And then it's
not smart yet. It just knows how to go forward. It doesn't know how to jump, but that's the, let's say, the very most basic thing that you can do to showcase that that the HFSM is running. So it is running that state, that specific action that we just created every frame, because it's part of the initial state and it never changed. It doesn't have any other possibility. So it's just doing that.
Exactly. Now, adding jumping is also pretty simple. So first, if we return to our bot here, we'll need another state for jumping, right? So one is move forward and one is jump. So just create a new state, name it jump. Now, what do we want to do in jump is we want to press the space button and jump. So this will be another action, right? So similar to here, we want to do something. So let's create a new action. Let's call it the jump action. This time it's putting it in the correct namespace. Nice. So this is again an AI action, and it overrides the update function. And then we can basically steal this here because we still want to move forward during the jump. Then in addition, we also want to update the jump button, right? So we have the jump button. I think here we want to call this update function. Like usually in Quantum, you can just assign a button like this. And then it processes the was pressed and was released. But since this is not the player input, we need to manually do that calling update, I think. So we call update, we pass in the frame number, then what we want. So when we jump, we want jump. And then we also want to reset this button when we're not jumping. So we move forward, we want to not jump.
Yeah, so Quantum basically has this, for buttons, it has an internal state machine based on what was the state of the button at this certain frame. So you just need to tell every frame what is the current state. You don't need to worry about was or is pressed or is down. You just say what is the current state, and then the state machine that's processed under the hood. Oh, that was a visual. You can just force the domain reload. You can right click on any script and then force reimport. Then it will reload the domain. Seems like a Unity rendering issue, maybe something specific to that version.
There we go, yeah. So it just, when this happens, I think you can just reload the domain. So reimport, exactly.
Yeah, I'll fix that.
Now, we have these two states here, but this is not going to do anything yet. What we need is a transition. So when we want to move forward to jump, we need to connect these. And then we need to go into this transition and define when this happens. And for now, we will keep this super simple. Let's just say we always jump. So we right click and we just choose a true decision. So this is always true. So this means we'll always move forward to jump. And then we'll also need to figure out how do we want to get back to move forward. And here we want to keep it super simple. Just when we finish jumping, we want to return, but maybe we want to add a little bit of a delay, stay a bit into the jump, so that we want to make sure that we don't double jump very quickly, because that might cause issues. So here there is a trick to this. So when we make a transition back, like this, instead of saying always, we can add a timer decision here. So this will add a little bit of delay where we stay in this state and then we return later.
And just to be clear, we do have a few pre-coded decisions and actions that you can use. So the timer decision is something that we already deliver with Bot SDK, which it basically counts a certain amount of time and then it starts returning true. So if you want to do delay decisions, just use the timer decision. It's already built in.
Exactly. And I think per default is 3 seconds, but we can also change this by introducing a new config variable. So this is going to be a constant. Let's just say we want this to be 1 second.
Yeah, and config variables are useful because you can create nodes out of them. And if you edit them on the left panel, all of the nodes will be updated automatically. So you can keep the consistency throughout your state machine just by setting up on the panel.
Yes. And now the last thing we need to do is call our jump action. And here we only want to really jump once. So we only want to press space once when we enter this space. So instead of on update, we can just use on enter. Now we don't have the jump.
Did you mark it as serializable?
No.
Maybe that's it. Yes, so every asset in Quantum has to be serializable for the bot SDK in order to create the actual instances and so on. So as bot SDK actions are always assets, you have to mark them as serializable. Otherwise, they won't appear on the editor, but we have a warning that tells you that, so you can take care about it, etc.
Exactly. So now we have jump action here. Can link that on enter. And then I think in an update, we can actually still say, let's just move forward, right? Instead of doing nothing with the inputs, we can still say, let's go into the forward direction. I think technically this is not necessary because we're never resetting the input source, but it also doesn't hurt. So now I think this should already work. So when we enter play mode here, you can see the bot jumps every 1 second. Then it stays in the jump state a bit, tries to jump again, and can actually go over the gap here and maybe even reach the end. So
yeah,
this stupid bot
just won the game, but he just killed himself. So yeah, he's not that smart, even when lucky.
Yep. So we can improve that, of course, but as you can see, it's already working. And we can also get a visual view of this. So if you want to see in which state we're in, for this we can use the bot SDK debugger, right? Here, the setup, I think the simplest way to set it up is adding the script here. And I think we also need to initialize it from the AI system.
It's either of those, because you can just add the script, and in Unity we already do all of the reflection and stuff in order to get all of the data that is needed. So you can do that on components, or yeah, you have to enable. You have to click on the little bug icon on the and then it registers properly. You can click on the game objects now. I mean, if you only add the component, the component on the game object, you have to click on the bot entity. Can you play again? I think that you didn't have it enabled before. The debugger, yeah, run again and then select the bot entity.
So
maybe I forgot something. You can do the initialization on the system.
I think that was needed.
Yeah, I might be forgetting that.
So I think we can just put it in here.
Can be.
Or fine if we call it multiple times. Bot SDK, buffer system. No, this would just be to add the entity, right?
Mm-hmm.
Yeah, we also need to enable the system somewhere, right?
Yeah. Yes. And it allows you to choose a label, so you can give nicknames to your bots. Did you call the bot SDK debugger system on the Quantum side?
Oh yes, exactly. That's what we forgot. Yes, this was what we're missing. You need to.
Yeah, because this is how the Quantum knows how to send data to actually make things happen on Unity. But it should be all fine now, either by selecting the game object, but you can show the screen, the selectable bot on the screen of bot SDK. That's also good.
So we no longer need this one actually, because we have added it by code. Now let's pin this one actually. Now we can select the bot here. And when we return, we see this little window here.
Yeah, so the thing there is that the bot is always in just one state, and as you can see, it's transitioning very fast from move forward to jump, because it happens instantly, because looks condition is just true decision. It always happens in one frame, and it's true already. But it takes some time to actually go back to the move forward, because there is a delay of 1 second. So that's essentially it.
Yeah, so it's a bit hard to see here, but there's like a one frame. I don't know whether you see it with the stream's compression, where it goes back from here to here and then around. We'll see it a little bit better, I think, once we add some more logic to this. So let's make the bot smarter and not just jump always. And this is done via a decision. So this is again an asset. Call it jump over gap decision. This is no longer an action, but an AI decision. HFSM decision, because these are specifically for the state machine.
I think you can increase the, yeah, thanks.
Then here we don't override update, but we override decide. This returns a bool, and true means we want to execute this transition, and false means not. Now here, what do we want to do? First of all, we only want to jump when we are grounded, because else we can't jump. That's like a super simple, very performant filter we can do. So we can grab the grounded component from the entity. And check, are we grounded? And if we're not grounded, we return false. And if we're not grounded, how do we decide to jump? And here what we want to do is we want to check, is there a gap in front of us? And so we need information about the world around the bot. And a very common way to do that is using raycasts. So that's going to be the approach here. And to know where to raycast, we will need the transform. So we'll grab that as well. And we will just grab the hits from the physics engine. We'll start at our position, maybe add a little bit of forward so that we don't want to jump when it's too late, right? We want to check down that there's something beneath us. And I think the other two parameters were the distance, which it doesn't really matter, let's say 2 meters. Layer mask, here we could actually just filter for the ground layer. So not sure how this worked with Quantum.
You can do frame.get layers if you want to use it, but
oh yes, it was in the frame, right?
you have to sorry, frame.layers.get mask.
Layer mask, and we pass in the name, and I think we called this ground in the Unity scene. We just put all the static objects in there. So this way we can filter for just the objects that we want. Then we can also say here that we only want to filter for statics, because here at the moment we're not interested in any moving objects. Maybe if you had like moving platforms at some point, you will need to change this, but this makes it more performant for now. So let's go with that. And then I think we just want to know whether we have a hit, right? So we can just return whether hits.count is larger than 0, right? So if we hit any ground, no, actually the opposite, right? If we don't hit any ground, so if there is a gap, we want to jump.
Correct.
So no hits means true, so we jump. If there is ground, then we return false, so we don't want to jump. I think this should already work, so let's try this out.
The ground is already set up with the layer, right? The ground layer.
Yes, I think so, but let's double check this. So no, it's actually not. These are all
you have, find the quantum component on them. It can be set, it should be set on the quantum component, or you can just hit statics instead of looking for the layer. That's whatever you want.
Oh, I think these are static colliders. Would be. Don't think we can.
I think it's gonna grab. I think it's gonna grab with the game object itself.
Yeah, let's try that. And else we'll just not check for the layer. Then let's go to our bot, go into the jump decision. We remove the true, and instead we will use a jump over gap decision. So now it's gonna run each frame where we could transition to this. So each frame we remove forward, it's gonna run this decision and check this. And then if it returns true, it's gonna move to jump.
Seems good.
Let's see whether this is working. So we are not jumping.
It didn't. It probably, well, seems like it found something. Let's see the code. So you get a position. Yeah. You simulate a position forward and then you recast down.
Actually, I think API for this debug.
Well, yeah.
We could actually make this a bit visible so that we don't make stupid mistakes like this. Oops. So we grab the position, direction. This is gonna show us a bit more in detail what the bot is doing, which is always nice.
Mm-hmm. Let's see.
So we get the raycast.
Are we forgetting something? I think we're forgetting something, Luke.
Yes. Is the ray long enough? Yes, it is, right?
Let's see
Something
that
isn't working.
did we build the HFSM? So we have jump over
Yes.
gap from move forward to jump should be fine.
Maybe we didn't build because it wasn't green here. But no.
You didn't. Maybe you're still missing something on the code. Should be something on the code. Let's.
Probably some stupid mistake.
So it's grounded. I assume it's grounded is correct, right? It is being set. So it isn't returning in line 13.
If grounded is false,
We
so if
don't
we're in
want to
the
jump.
air, we don't want to jump. This is correct, right?
So you get the transform, you do a forward, and then you recast down.
Well, let's just try without this. Can
I think
it
you have
possibly
to.
default
Maybe
here?
it's -1.
What's this say? Yeah, -1.
The default value, I think.
So here.
Is it -1?
Just barracks. Here is my minus key. There.
It looked like to me that it didn't try to recast. Not sure. You can double check on the state inspector if it's grounded is set properly. When you run the game,
Oh,
to see
maybe
if the
there is a
components
problem with the ground check system.
Yeah, but yeah, let's see.
We're jumping
Well,
now.
it's jumping,
but too many
except that
times.
it too soon, so it thinks there is a gap. Maybe it's the layer thing. Maybe -1 isn't the default, then it's not finding the ground itself.
I think this one at least, it has -1 as the default value.
Yeah, okay. How do we have it there? It's statics. Well, let all of the computing happen. Yeah.
But this means we also hit ourselves, so we would need to add a filter here. So let's just try to rewrite this a bit. Let's say alt, we can just iterate over each bit. It's hit, not dynamic. So if you're not hitting an entity but a static collider, then let's say we hit ground. And we return hit ground. Let's see whether this works. Else it's maybe something. Distance of 2, position forward. I think this is looking fine.
Should
But
be.
the array looked a little bit short in the debug view.
Still did. Too soon. Let's check code. So okay, you have let's not do okay. So you have the position, and then you go a bit forward, and then it's meant to be down, and choose the length. You can remove the last parameter as we're anyways letting it be the default.
Yeah.
And then for every hit, if the hit is not dynamic, then it hit the ground. Should be good. Emo should be all fine. Well, but it's probably finding itself, or yeah, it's probably finding itself. So you can
But we're not
say,
dynamic,
but you have,
right?
yeah, it's not dynamic, yeah.
So maybe it's still something here.
And that looks good, Emo.
But I'm just wondering, because we're drawing this array, right? But I don't see it here. Like it only shows up very rarely.
Yes. I don't know. Let's see code again. That's probably a small mistake there. So if it's not grounded, that seems good. Return hit ground. So whether we did a hit or not, so it's usually false, meaning that we didn't find, so we should jump. Hit for every hits. There's a distance. It looks all good to me.
Yeah, the code looks fine.
If it's not dynamic.
So when we
did we
debug
forget
this, it's really
it's just trying to jump too much.
Yeah, it moves into this jump state. So maybe let's just attach the debugger, see what's going on here. So what we care about is really returning true, right? So
yeah.
Where did our ball go?
Maybe it finished the game. Rerun, maybe.
Okay. So
it thinks it hit. Yeah, it should be good in the beginning.
Oh wait, oh yeah, this is wrong.
What?
Do you see it? Well, we jump when we hit ground. We want to jump.
Oh.
This is silly.
Yes, that was very silly. Yes, sorry for not seeing that before. So we only want to return true in that decision if we didn't find ground. So you have to have that in mind. True means success. We inverted the condition there. Now it should be everything good. Yes,
now
so it's not jumping because there is
the
ground underneath it.
And now it jumped.
So it only jumps on the gap and never anymore. That's fine.
Now it still struggles a lot with these AI balls. So let's also jump over these. That's probably a super simple way to solve this. So I think we can just copy the jump over gap decision. Jump for NPC. Let's just grab this code here and just adjust it a bit for the NPCs. Again, if we're grounded, we don't need to jump. And then here, when we go through the hits, we no longer want to check the ground, right? So here we want something that's dynamic. Then we'll need to adjust this part here a little bit. So First, let's give this another color so that we see it in the scene. And when we jump over the NPCs, we want to look forward, right? Is there something in front of us? And here it's a bit special because there is a slope. So this floor here, this one, it has a 15-degree angle, right? So let's raycast into that direction. Now, 15 degrees, it's like roughly a 25% slope. So we can just create a rough approximation of what we want with this. So this, no, we want.
It has to be on the Y, yeah.
Yes. And then for each one forward, we go 0.25 up, exactly. So this casts roughly at the same angle as the slope. Then instead of down to direction, let's say...
Yeah, you can normalize it to let the length be controlled by the raycast itself.
Oh, yes, exactly. This is direction, so we need to normalize it. That's a very good point. Call this hit. See? And maybe we'll need to go over this again. So if we hit something, if it is dynamic, we say we hit an NPC, and then we want to jump when we actually hit something. So this time this is correct. And then here we also need to make sure that we're not hitting ourselves. And I think the easiest way to do that is to just compare the entity with our own entity, right? So just do entity not equals entity. Dynamic.
I think in this case it won't, because the raycast, when it comes from inside something, I think it ignores self. But yeah, let's do it anyways.
Oh yeah, you're right. Maybe this isn't even needed. But also shouldn't hurt much.
Yeah. Now it's still gonna be a little bit of luck because it doesn't steer right and left and right, but yeah, anyways. Yeah, edit state. Now you can hover the button, exactly. Yeah, then enter, and so there are now two ways of going from moving forward to jump. One of the ways is detecting a gap, and the other way is now detecting an NPC in front of you. So that works like an OR operator. Either of these decisions will take the bot to the jump state.
Yes, and you could also just use a OR decision here and plug them into the same transition, but let's keep things a bit separate here for now. So let's see how our bot does.
I don't see that first. Jump over NPC. Yeah, it tried. It's still bumped, but it's still trying to jump. Just too many force bumping him backwards. And then he tried to jump and then failed.
I'm actually not sure
sideways.
Because this should have a raycast. Whoops. I don't see the visual part.
Oh, the raycast itself. Maybe it's just gizmos related. Maybe you have it disabled.
Oh, yeah. No, I probably didn't update the gizmo code. Yeah, this is still... No, this is still broke. So this needs to do the same thing.
Correct. Direction times 3, yeah. So
that means it's actually working. I think we also saw the bot finish the thing. So
did it rebuild? I think there was a... I didn't see the okay, that's going on.
I think I pressed play too quickly.
Yeah, it didn't have time to reload the DLLs.
Yeah,
but it should be fine now.
Now we see the direction vector. Maybe we could even make it... Like, it could be a bit longer, maybe, right? So
yeah, so the prediction is happens earlier, right?
could also make this velocity based. So, right, it depends a bit on how fast is the NPC approaching and how fast are we.
Yeah, so that's all possible. So you can improve that decision a lot. So it can be very smart. You can even see, hey, maybe on that ball, there is also another one coming from the left. Now I want to steer to the right to run to both of them, and I don't even need to jump. So yeah, this can get complex, but this is a simple demonstration.
I think for now, let's keep it like this, keep it simple. And instead, like now we have these bots here and we can like even duplicate those. But it's not really related to players yet, right? So what we want is, like one thing we talked about is backfilling the room with players, right? So we want to see how many players would you like in the session and then fill the rest up with bots. So I think that's one of the things we can do. And the other thing is really replacing the player object with a bot.
Yeah, let's do that. That's really important usage.
So I think we'll start with this actually. So we'll add a component which helps us control that. Let's call it bot setup. Oops. Got to name this qtn file. And this will just help us set up the bot. So what we will need to know is which root, HFSM root do we pass into this. So we will need an entity ref HFSM
No,
root.
you're confusing. It's asset ref.
Oh, yes, this is an asset, not an asset ref. And then let's also just add functionality to like initialize this on start, right? So not on start, but on component edit. So this will just allow us to immediately replace a bot with the component.
You missed an I, yeah. Ini, yeah.
There we go.
Yeah, so essentially you want to give a few options. So maybe you want to force this bot to work already right away as a bot, or maybe you just want to, usually you get a component and add a few options so you can toggle it on the fly. So it makes testing easier.
There we go.
Correct.
Need to capitalize this correctly.
Yeah.
Now let's add a system, which for now, let's just do this hard-coded one where we can force the player to be replaced with something. Call it player bot system. This is a signal only. And we say on component edit, bot setup, we do something. And here we want to basically replace the player's controls with a bot, right? So we will need the root. That's ID, and then we'll need to create a new agent component and add this root to it.
Yeah, so essentially what Luke is doing is, okay, we want to set up the bot during runtime instead of before runtime. So we can with Quantum create a component and add it to the entity right away. It's very cheap. It doesn't, it isn't expensive CPU wise. So that's what Luke is doing. Okay, if this bot should be, if this entity should be a bot, let's create the components right away, which is the HFSM component. HFSM agent components, and then we initialize it with the HFSM manager as we just did in the past. So, and then after we create the component, we can actually add it to the entity itself. Oh, you're adding the asset. You should add it the agent.
Oh, the agent. Yes.
So now this entity is also an HFSM agent.
Yes, and then we can also add it to the debugger, right?
Yes.
We want to.
So from their point and on, every filter that uses HFSM agent as its main component will find this entity because we just added the component to it.
Yep. So let's add this to the system setup. Here down with the signal only system. Let's just check real quick whether this works.
So we shouldn't see much
Each
difference
player will
now,
get this
right?
bot script.
Mm-hmm.
I think we can use. Oh, actually, we made a mistake here because this is always running. So we only want to do
so
this if we're
everybody will
forcing
be
it.
bots. Correct.
Yes. So.
Yeah. So if that's false, you return. So we will only force to be bots the ones that in Unity we specifically say it on the component. Initialize this when it's added. Otherwise, this is supposed to be controlled by a real player.
Yeah, and I think let's just also add the connected and disconnected. So there are two callbacks for this.
Quantum callbacks. So they are triggered for when a specific player isn't active in the simulation at the moment and when it is back with activity. So it essentially helps us knowing, okay, if this was triggered, this means that the player got disconnected. And that's exactly when we want to set up that player as a bot. So that is how easy it is for you in Quantum to know that a player just isn't playing anymore. So just control it with AI. You just listen to the player connected and player disconnected callbacks and add and remove AI accordingly. It's very, very simple.
Yeah. So what I'm doing here is I'm just putting this logic here into a separate function. And then when a player disconnects, we can basically also call this function here. There is one thing here, we need the entity, right? So we'll need to fetch the player's entity here. There are some patterns to do this. Like one thing you can do is store those into a dictionary, right? So that you have a quick access to each player object. I think here we're just gonna do a simple search because it works. So let's create a function for that. Then I think we just get a filter for each player, right?
Mm-hmm.
So we
have this player ref components, the player link components in every entity. Then as we are doing ECSE code here, we just go through all of the components of this type player link. And it's the one who knows what is the player reference that that entity, let's say, owns, under quotes. So when we find the entity which has the player ref that corresponds to that player who got disconnected, then this means, okay, this is the entity that that player was controlling, and now this should be controlled by a bot. So that's what Luke is returning there. He finds it, and then he returns the entity. That's the player entity. Now he's going to get it with the function. And then he can call his same logic for replacing an entity by a bot, a player by a bot, just by calling it again, reusing the same method from before.
Yes, and here the default check, that's similar to null check, but this here, it's a value type, right? So you can't check for null. Instead, you check for default.
Mm-hmm. So essentially getting the things that the method needs.
Call this an entity and not an object, because this is not an object.
Let's not confuse people with the technical C# terms. Perfect.
So when we disconnect, we replace the player with a bot. And when we force this via the bool, we are also replacing it with a bot. And then the thing that is left is that when we reconnect, we'll want to remove this bot component again from the player, right? So reconnect is going to be simpler. We're just going to say frame.remove component. And actually, we'll need to search for the player object as well here. So if we find a player object, let's remove the bot component from it, so the HFSM agent.
Yeah, that's important because maybe that player is just a late joiner who was watching. It's just a spectator and doesn't have an entity in the game. So maybe we don't even need to give control back to anybody. It depends on the type of player.
Yes, and I think there is one thing left to do here, and this is when we replace this with a bot, we're still leaving the player link on there because we still want to know who belongs this to, right? So that we can search it on Reconnect, but we don't want inputs from them. So here in this player input system, I think we want to really check for like, is this thing a bot, right? So what we can say is if frame.has agent, return here. So this means we're only going to grab the input from the player when we don't have an HFSM agent. There might be a little bit nicer ways to do that, which are a bit more decoupled, but this is super simple. So let's just do it like this for now. I think it should already work. So let's try this.
That's like now. With 5 minutes of coding, we already have the replacement.
Yes, this works super fast. So the hard part will really be to create a good bot. But as you can see, these are already pretty good. Like they'll probably beat me at playing. This sounds stupid, but yeah. So let's go to our player at the bot setup and let's give it correct state machine. And then let's keep this false for now. But I think we can just check whether this here works.
Yeah.
So let's have two of these. Let's say they initialize on component added. Now, this seems to work, but we're also getting an exception. So we'll need to figure out what's going on here. This seems to be the entity view. Oh, okay, it's the player color. So we have this script which I think it sets the color of the player. This is super simple, but
yeah,
it needs a player link, and we don't have a player link. So this is just because these are scene objects, and we're not adding them manually. So let's just add a player link. Now it should work. No.
I think that was the multiple selection. You can't add components with multiple selection. So one of the entities didn't receive it. Yeah.
Exactly, you're correct. There we go, no exceptions. These two are bots. But now let's try the connect reconnect thing. So here we want to go in multiplayer actually. So we will use this built-in menu and we'll also build an additional client, right? So that we can join this client and then disconnect it and see the bot take over that client. Because that's really what we're here for.
And it works flawlessly. It's also trustful because the whole disconnection systems are based on verified frames. So there's no issues with prediction, wrong prediction and stuff. It's really trustful info that we know for a fact the player just got disconnected. So it's very useful.
So when you play here, we have two players. And each player can control their own player object. And both of them are not bots, as you can see. But now if you press this disconnect button here, the blue ball starts to roll like a bot and it jumps over the gap and everything. And now the cool thing is when we reconnect, we're also gonna take back control over this, all right? So it fluently works and takes the control from the bot.
For me, that's awesome. Like when you can do such type of thing, like in 5 to 10 minutes, and that's so important for many online games, right?
Yeah, because it's really fluent. People won't see it. So if someone disconnects, it just people don't realize it. They think it's still a real player if the bot is halfway decent. So the other bots, they actually made it to the top. So that they work quite well, apparently. They can solve this puzzle. So that's all working. Now, right now, we just have a hard-coded amount of bots at the start, right? Which is a bit lame. I think what we can do is we can always have the same amount of players in a match. So let's remove these for now and add a new system to actually do that. So let's call it fill room system. It's gonna be on the system main thread, and we wanna check, like, first of all, how do we approach this? We wanna spawn some player ones, right? So let's add a function for that. This we're gonna call once, so we'll need to add some logic that this doesn't run every frame, but let's do this later. And then here we say for each player, gonna iterate over them, and if they're present, we don't need to do anything. If they're not present, we're spawning a bot for them, right? So an easy way to check that is via input flags. This is the player input flags. Then we say if we're not present, and these will be, this is an end logic. So we just activate this one bit here, and we want player not present. Then if this is equals player not present, so this means only this input flag is set, and we're not present, right? Just a bit of simple bit arithmetic here. Not present, we want to spawn an entity. Now we'll need to get the prototype from somewhere, and I think a simple way to implement it for now is just put it into the runtime config. Or what would you say, Juan?
Yeah, that seems good enough, because that's the purpose of the runtime config, is to, for that session, what would be some specific configs. It doesn't need to be player specific, so it doesn't need to be in runtime player, but of course some games can do that with runtime player. If, for example, the chosen bots depends on the character that the player chose on the menu, or maybe on the level of skills of that player, we're gonna put up a harder bot and so on. But in this case, we're not doing anything player specific, so it can be on runtime config indeed.
Now there was a function here which we needed to override, right?
Yeah.
It's called serialize.
Yeah, it's serialize user data, actually.
Serialize user data?
Yes.
Isn't that the one on here? Oh yeah, okay, right. So this is important because these are serialized by Quantum, and actually the state of them is sent over the network. So you'll need to make sure that you serialize these correctly. So this will serialize the ID and add it on every machine so they match, because else this will be default when you start Quantum. So that's not what you want. So let's return to our fill room. And now we can just grab here the prototype, right? So this is on frame, runtime config, player prototype. Then we can instantiate, well, create an entity from this. Then here, what we want is we want to force the replacement, right? So I think the easiest way for us to do that is actually just call this function here. Because we would need to initialize that component, but this value is set to false by default on the player. So that get a bit complicated. So let's keep it simple. Just call that function. Frame, bot setup, and entity. There we go. Now we don't want to call this each update here. So we need something to hold state. This could be an entity. Another way is just to create a global state. So this is usually not ideal, but oops, this shouldn't be a C# class. It should be a quantum file. QTN. So what you can do here is you can just say, I think it's this syntax, right? Let's say we have a bool which is, did we fill the bool? Doesn't like this. Bubbles. Could you try figuring this one out for me, Juan?
It's just global, no globals. It's not in plural.
This also doesn't work.
Okay, let me see. So you.
Oh, maybe it's global. Matter? No. So yeah, we'll figure this one out. Can you check the doc real quick? But yeah, the idea here is if global, the value which we'll get, if this is false, then we set it true. And then we will fill the room, right? So this ensures that this only runs once. Then actually what we can do is, once we have run this, we can actually disable the system, because else we will check this each frame, which is a little bit of a waste of CPU resources. I mean, it's gonna be super quick, but still, this makes it easier. And then the other thing we want to check here, we don't want to do this necessarily on the predicted frame. It's not necessary for something like this, and it's just going to simplify this a bit. It would work, but it doesn't have to be. So let's just do this once we're sure that this is a verified frame.
If it used predicted, it could include some jitter from network issues and stuff. But yeah, so in either way, the safest way to do this is trusting the verified frame. Now that seems all good to me. Are you sure the error is on that class? Try rebuilding.
It's global.qt
Namespace
and a namespace cannot.
Oh, you maybe created an extra file somewhere by accident, because
but it says global.qtn.
Is it
well, if you remove this, so this works, right? So this compiles.
Yeah.
Oops. So this compiles. If you keep it empty, it compiles. Then if we add stuff, it breaks. So it doesn't like something about this.
Are you sure? No, that's all okay. I think there is something when you created the file that you created a C# instead, and I don't know.
Let's just kill this, start from scratch.
Yeah, call it fillroom.qtn just to be sure that we are not clashing with something that was created in global.
Global. And we add a bool. Fill room.
Yeah, that was it. That was some weirdness when you created the C# instead and something remained.
Yeah. Now you can just access this via frame.global build room, right? So you can have many of these globals, and it's just gonna put all of them into this single one here. It's very convenient, but it's also a bit too convenient, so you might not wanna really use it for too many things. Now this one will also need to be added to the system setup. Doesn't really matter where. And this fills already the room with the correct amount of players, because this player count, it's gonna be whatever you have defined as the player count for the
It's the
game.
total.
Quantum. So we will get 6 players. Yes, exactly. There is an exception to this, which is the Quantum Debug Runner. That one overrides the player count, right? So here the player count really depends on how many players you add here. But if we start from the menu, it's gonna take the correct amount of players, right? As you can see, there are 6 slots here. So when we enter the game, we forgot something. We'll need to, when we edit this config here, we will need to link this up, right? So we made changes to the runtime config.users, but now we'll need to actually provide this prototype here. So this is the player avatar. Let's try again. There we go. We have our bots. We can play as well. And yeah, it just feels a bit more like a multiplayer game now, right?
Beat them.
They're really good.
Third. They're good. Oh,
I told you they're good.
Yeah.
So
sometimes randomized actions are the best.
now we're still getting an exception. So,
yeah, should be related to player links and stuff like that, probably.
Yeah, it's probably something with the entity view. Player color again. Oh, no.
He's trying to access from the player avatars, the links.
Oh,
yeah, because
yeah, it again.
You
Again
didn't
wants to get
to
a player link. So
well, you can have some if has player link, then proceed instead of already grabbing. Yeah, so before that line, just if.
I think we're actually doing that in the camera. Yes. So here we're doing this, where we're saying if we get the player link, then let's continue. If not, then let's not. So we should be doing that here as well, right?
Correct.
One important part here is we're checking here for the verified frame. So this works because of the bind behavior. So this is set here in the entity prototype and the view, I think. Is the bind behavior, and we'll need to switch this to verified, because else they will also be spawning the views in the predicted frames. And then when we get this onEntity instantiated function here, the entity will not already be present in a verified frame, right? So you'll really want to switch this for something like a player object where you don't need to predict the spawn, and else the logic in here becomes a bit more complicated sometimes. But yeah, let's just keep it simple for now. So yes, there we go. We have a room of bots filled up by players. We still have the functionality we had before, where if you disconnect, it adds a bot to you. So this already really feels more like a multiplayer game that is alive, that has a community playing it, and that is really important. So when you release your game and at certain times there might not be many players around, this really helps them to get started and have more fun in your game, right?
For sure. And on the game jam, it seems like it will be very important. So because it's going to be hard to get people to test.
Yes, and also there is a prize category for this. So if you implement a good bot, you have a good chance of winning a prize. Yeah, you shouldn't participate for prizes into a game jam. It's really just for the fun. And as you can
Yes.
see, when you disconnect it, it replaced this blue player with a bot. So yeah, that's still working. So when we reconnect, we're now over here. So yeah, I think that's really all that we wanted to show you guys today. We're also a bit over time, but I think it was worth it because we just were able to show you so many nice features around the bot SDK, right? Your game might need a bit of a more complex state machine than what we have here, but
Or behavior tree.
or a behavior tree, exactly. So you can dive into the docs for that. We also do have a sample for this, right, Juan?
Yes, so we have it's a technical sample, meaning that it's not exactly a game sample where you have winning conditions and stuff like that. So it's just a technical sample meant to show you the very basics of how to do the initial setup and testing. So we have this sample scene with HFSM and behavior tree, where we have these little NPCs and they have to collect a gem and then deliver to a box. So I think it's more or less 6 states. It showcases delayed decisions, showcases using many types of actions and finding stuff that we want to chase and actually delivering them to some place. So yes, we do have the sample, and it's interesting if you want to go for the bot SDK, make sure to start with that. The bot SDK itself is not categorized as a very, 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 very beginner sample, tool, but of course you can use it as a very beginner or as an expert, because AI difficulty ranges from whatever it can be.
Yes, exactly. And you can also go over today's stream. So this will be uploaded as a VOD on YouTube. So here we're really just going step by step through this very slowly, right? So if you're running into an issue, just check here on the stream, where you could have messed up, and hope that really helps. Else, we're always active on the Discord, both on our own Discord and on the multiplayer Game Jam Discord from Global Game Jam. You can reach us there to ask questions about Quantum or the bot SDK. And I think with that, we're gonna call it a day. Thank you so much all for attending today's stream. I hope you were able to learn something new about Quantum and how to implement bots and drive player engagement with them. And a special thanks to you, Juan, for sharing all this information with the people here.
Yeah, thanks everyone who watched. Thanks, Luke. And yeah, if anybody needs help, we are available on Discord.
Yep, with that, have a wonderful day, guys. Goodbye.
Bye-bye. See you.